Hey everyone, welcome back to our Calculus 3 class notes. We're now moving into section 15.5 and we're now going to talk about triple integrals. So we've been talking about double integrals, and first we're going to talk about triple integrals in rectangular coordinates. So triple integrals, if we have a function f of x, y, z, that's a function defined on a closed region D, capital D in space, such as the region occupied by our Herbie the whale here, then the integral of f over d may be defined in the following way. We partition a rectangular box-like region containing d into rectangular cells by planes parallel to the coordinate axes. So you can see these basically get these small little cubes. You have a delta in the y direction, you have a delta in the x direction, you have a delta in the z direction. So it gives a little delta v, a little small volume inside this, underneath this function, if you want to think of it that way, filling the volume that this function z equals f of x, y makes, if you were to imagine it being solid. Okay, we number the cells that lie completely inside D from 1 to n in some order. The kth cell having dimensions delta x sub k by delta y sub k by delta z sub k, and the volume delta v sub k, which is delta x sub k times delta y sub k times delta z sub k, as I just got done explaining and pictured here. Then we choose a point somewhere in that cell, and it doesn't matter where, it just has to be in this cell here, this little cube. And we're going to shrink these deltas down to 0 anyways, which will force the point to go to the middle of the cell. But we choose a point in that cell and in each cell and form the sum, the partial sum. The sum as k goes from 1 to n. So n, we'll eventually let n go to infinity, which effectively shrinks the deltas down to 0. But right now it's a partial sum stopping at n. K goes from 1 to some of this function in that volume. So the function times the volume, right? That little delta v. You then let the volume of the largest of these cells approach 0. Or put it another way, we let the number of these cells approach infinity. This limit is called the triple integral of f over that domain D. So the limit of the partial sum s sub n as n approaches infinity is now the triple integral over the domain D. Now the domain D is a three-dimensional domain of f of x, y, z dv. So dv, if it's rectangular, we're going to integrate with rectangular coordinates, is just dz, dy, dx, or any order that works. So the volume of a region in space then, if f is the constant function, 1, then I'm just adding up all those little volumes, right? So then that becomes, then the sum reduces to just adding up all the little volumes. So as delta x sub k, delta y sub k, and delta z sub k approach 0, the cells become smaller. The cell volumes become smaller and more numerous, and they fill up more and more of D. We therefore define the volume of D to be the triple integral right here. Okay? Okay, so I'm going to move on to example, but let me do one more video, do that in another video.